So again, I'm recording this so that if you do miss something, you can come to that section you missed and you can go back and make sure you got the information you're looking for. Notice on the beginning of all these slides, there are recommended problems that are in the book so that you can do those in addition to the ones online. These are not graded. This is just to help you kind of work through it. Okay, yeah, Daniel has a comment there in the top there. So if you were looking for a private tutor, please go through Slack. They are available to you for that. Okay, welcome back. We're going to continue on with our chapter 12, part 2. So the first part of this was creating an alcohol from a carbonyl compound, and we introduced ourselves to 2 reducing reagents that are very selective, okay? The lithium aluminum hydride, which takes carboxylic acids and carboxylic acid esters down. We'll learn in the amine chapter, it also works with amide compounds as well. But then we learned that the sodium borohydride is selective to aldehydes, ketones, and the acid chlorides, okay? And that you could put in a reagent and reduce down an aldehyde selectively in the presence of that ketone because it reacts faster, okay? So now we're gonna go the other direction. We're gonna talk about how to oxidize alcohols to carbonyl compounds, and we're gonna do it in such a way that we have that same theme of selectivity. We really want to think about in each of our reagents, what is selective about them? What do they do better than other things? For example, can I make just an aldehyde? Can I make just a ketone? Those are the things that we're looking at for our reagents here. We're trying to pick those reagents to give us exactly what we want, okay? So let's go on to the oxidation here. And so in alcohols, we have 3 different kinds of alcohols available to us. We have primary alcohols, which have 2 hydrogens on the carbon with the OH on it. We have secondary alcohols, which have 1 hydrogen on that carbon with the OH on it. And then we have tertiary alcohols. And those have no hydrogens on the carbon with the OH on it. And I want to start with this one first because those are very hard to oxidize. You have to break a carbon-carbon bond to oxidize those materials, or you have to do some kind of chemistry on a carbon other than the one the OH is on. So we typically don't oxidize those down. If we do, we use some special reagent where we're trying to get down to a carboxylic acid anyway. So we're not gonna have anything for this particular. So let's talk about these primary alcohols. Now, primary alcohols, because we have those 2 hydrogens, we have 2 steps. We're starting from an oxidation state of -3. We can remove 1 hydrogen and add a second oxygen bond and get us our aldehyde, or we can remove 2 hydrogens and get us a 3rd oxygen bond, okay? So that gets us to where we have H, R, O, H. Okay. So it's these 2 hydrogens here that I'm about to circle in blue are the ones we get to play with here. And if we only want to oxidize 1 of those off, we can get to our aldehyde by having the electrons in bond here come in and give us our carbonyl compound. We still have our single bond to hydrogen and then our R group here. Or we can continue on oxidizing it down a little further and reduce off that last hydrogen to give us our carboxylic acid, okay? So when we think about doing this on whether we stop at the aldehyde or get the carboxylic acid, we have to think about selectivity. So we are going to come up with a special reagent that'll stop at the aldehyde, and the other oxidizers will take it all the way down to the carboxylic acid. So we need to pay attention to that, okay? Now, luckily, when we talk about ketones, we only have 1 hydrogen that we can oxidize off, and it has to be this hydrogen and this hydrogen to give us our carbonyl. And so it really doesn't matter what oxidizer we use. As long as it's an oxidizing agent, it'll take it down to the ketone, okay? So if we have a primary alcohol, we have to think selectivity. If we have a secondary alcohol, we can use any of the oxidizers we have available to us in this chapter, okay? So it's all about what you have to start with, how many hydrogens you have available to you, okay? So the first set of oxidizers I want to talk about are the chromium oxidizing agents. Now, all of these typically use chromium in its oxidation state +6, and it uses it and it will transfer oxygen off of that chromium onto the carbon substrate. And we have a few different versions of this that we can use. We have what we call chromic oxide, which is CrO3. And then we have things called sodium dichromate and potassium dichromate, okay? Notice those are Cr2, which is where the dichrome comes from, dichromate. Okay, so it's Cr2, but the oxidation state is still in its +6 form, okay? Now, these are really good, strong, non-selective oxidizers, but they are typically used in aqueous acid, okay? You have to add some kind of acid to activate it, and they're always done in water, okay? So you have to have an alcohol that dissolves in water to be able to use one of these two reagents, one of these three reagents, okay? So the next chromium-based strong oxidizer is what we call chromic acid, okay? And it's basically, you've taken this chromic oxide and added one equivalent of water to it. When you do this, it can dissolve in certain things like ketones or carboxylic acids, and you can then use it as a strong oxidizing agent, but it's already protonated. Notice it has those hydrogens there, and they're up where we see like the hydrogens in sulfuric acid. So you don't need to add any additional acid, but it does dissolve in a lot of different organic materials. So if your alcohol does not dissolve in water, you can get it to dissolve in typically a ketone, and you can get this chromic acid oxidizing, okay? Now, the third oxidizing reagent we want to talk about is called PCC, okay? Which stands for pyridinium chlorochromate. So I'm going to draw the structure for you here. The key with this one is that having the chloride on the chromic acid changes its oxidation. It makes it slightly milder, meaning it's more selective, okay? So if we look at the chromic oxide-based ones, they all have this similar structure in place, where we have this chromium on the plus with 3 oxygens around it in its +6 oxidation state. It transfers those oxygens off, and it's very, very aggressive, okay? And then we have, so this is basically all of these have that as the active species. Then we have our next thing, pyridinium. And pyridine, as we'll learn about in our chapter 14, is one of our benzene derivatives, but it's going to be made into a salt. It's going to be protonated by HCl, and the chlorine is going to be attached to the chromium. And so what you end up with is chromium still in its +6 oxidation state, but it now has a chromium-chlorine bond. That chromium-chlorine bond lowers its oxidative strength. Because it has a lower oxidative strength, it is selective. And so we get this compound right here will stop at an aldehyde, PCC. Now notice it's usually done in this compound here, CH2Cl2. That's dichloromethane. It is just a solvent. It does not participate in the reaction. It's just a very good solvent. So especially for things that have that are very poorly soluble in water or in acetone, this is a very good reducing agent to take things down to aldehydes that would otherwise be insoluble in water solutions, okay? So how do we use these? Well, all of these reagents will oxidize secondary alcohols to ketones, okay? So if we have isopropanol, OH, we can use the chromic acid, we can use the we can use the sodium dichromate right here, and that'll oxidize it down to our ketones. And turns out PCC is still oxidative enough to take any secondary alcohol down to a ketone as well. Okay, so it'll react with primary alcohols to give it aldehydes, but secondary alcohols to give it the ketone. Okay, so let's talk about primary alcohols in a little more detail here. Okay, if you want to stop at the aldehyde, you must use the PCC. Okay, it's the only one that'll work for that. Otherwise, it'll keep oxidizing it down to a carboxylic acid. Okay, so all of these chromium-based reagents, and all of these are equally reactive as far as oxidation reagents go, can reduce down our primary alcohols down to our carboxylic acids. Okay, and notice these are all typically under acidic conditions, meaning you get the free carboxylic acid at the end of the reaction. There's no reducing step or hydrolysis step required. Okay, now this works for things that are soluble in water or occasionally a ketone here. Okay, if your compound is not soluble in acidic water, you might want to use another oxidizing trick. And the next oxidizing trick to use is what we call the potassium permanganate oxidizer. Okay, the reason the permanganate oxidizer works for some alcohols and not others is because it's done under basic conditions. Okay, notice it has hydroxide here. Okay, so in basic hydration, in basic conditions, you can take a alcohol that's not very soluble in water, deprotonate it with your base to give you the salt right here, which is then soluble in water, which then can be oxidized to, in this case, a ketone right here. But if this were a primary alcohol, it would be oxidized down to the carboxylic acid. But it'll reduce it down to ketones or carboxylic acids, depending on whether it's a primary or secondary alcohol. Okay. Note, this is done under basic conditions, so you have to acidify as your final step to yield your protonated carboxylic acid. Okay, so now we've been able to go from a primary alcohol to a carbonyl compound to alcohols. Okay, now how do we kind of confirm to ourselves we actually did those reactions? And that all comes down to spectroscopy. So when we have carbonyl compounds, we have a strong stretch in the 1600 range. When we have alcohols, we have this big, broad OH peak here in the 3000 to 3600 stretch. And the broadness comes from the fact that it hydrogen bonds to itself. And because it hydrogen bonds to itself, it makes that really big, broad peak. All the other peaks we see here are carbon-hydrogen peaks and carbon-carbon peaks. So that's the only functional group that happens to be in the system. Okay. If we look at proton NMR, and these first three are proton NMRs, we see that the OH by itself does have a signal for that hydrogen on the alcohol here. However, because it hydrogen bonds, it'll exchange very quickly with deuterium oxide. And so that will make the signal go away. So you can actually positively identify which peak is your OH peak, because number one, it'll be broad. Number two, it'll go away as you add deuterium oxide, okay? Now, for all other hydrogens that are adjacent to the alcohol here, we see a shift to about 3.3 to 4.0 ppm. And that's because those hydrogens are being de-shielded by that electronegative oxygen, and that's shifting them up above where we'd see them for regular CH3 group, which would be closer to 0.9 ppm. So we're seeing a shift up to approximately 4 ppm. Okay. If we look at our carbon NMR, which is this last one here, again, that presence of that electronegative oxygen shifts it up from where we'd see it at 20 to 25 ppm up to 50 to 90 ppm. Okay. So that's how we would signal the difference from going from our carbonyl compound to our alcohol by looking at its proton and carbon NMR as well as its IR spectrum. Okay. So that is the end of that portion of the lecture. Now, if you have any questions, go ahead and put them in the Zoom chat right now. After that, I want to start talking about strategies. And what I want to do is I want to do an exercise where we go from one compound all the way in a circle to back to where we started from, and do that on 2 different compounds so that we can see our strategy for synthesis. Okay, I think I want to start here. So I'm going to erase this set of slides right here, and we're going to do a strategy. Okay. Oops. Anyway. Okay. So, all right. So now let's all talk strategy about how to do this. Okay. So when we're thinking about the 4 reagents we just learned about, okay, well, technically 5 if you think about the permanganate right here, we can selectively go from one place to another and arrive at the same point by going around in a circle here. So let's start with this reagent now. Let's start with this right here, okay? So we have 2 different carbonyl compounds here, okay? So we know that one of them is an ester. So if we wanted to reduce that down selectively, we can't do it because we know that we have to use lithium aluminum hydride to reduce down this compound right here, but that would also reduce down this, okay? So if we were to use lithium and aluminum hydride on this particular material, we would end up with a secondary alcohol and a primary alcohol on our system here. So this is lithium aluminum hydride. And remember, we have to use it in something like ether because it reacts violently with alcohol and water. And then our second step is quenching it and then acidifying it to make sure we have our protons back on our hydrogen. So we can get to a secondary alcohol or a primary alcohol using that. However, if we just wanted to reduce down the ketone, we have to use our different reagent there. And we can use sodium borohydride. And it'll give us our carboxylic acid ester. Actually, it's not going to clip our ester off. Right here. So we can selectively get to that point. Now, because we have this secondary alcohol and this ester here, we can actually use almost any reagent to get back to this ketone. We can use PCC because it oxidizes down secondary alcohols to give us ketones. We can use permanganate because it's going to oxidize down that secondary alcohol to a ketone. And we can use any of the chromium reagents right here to convert to that, okay? Now, What we'll find out in the carboxylic acids chapter that the permanganate, because we're using base or a lot of water here, might not be the best reagent. But we'll look about that when we get to that chapter. Okay, so what can we do selectively to this compound here? I'm going to erase these reagents here. So we have a secondary alcohol and we have a primary alcohol, okay? And as we learned, all of our reducing agents, all of our oxidizers will convert that to our aldehydes or ketones, okay? Right? So, but what we can do here is we can look at it selectively as well. If we take this and react this with PCC, we'll get an aldehyde and a ketone right here. But if we take this and react it with chromic acid or any of its chromic acid derivatives, we'll get a ketone and a carboxylic acid. Okay. So now do you see the reason for the selectivity of these reducing and oxidizing agents? Choosing which reagent you use in which order chooses your final product, okay? So we can reduce off our ester and get to our two different alcohols, and then we can turn it into an aldehyde and a ketone, or a ketone and a carboxylic acid. And then we could even take this and reduce down just the carbonyl here to a primary alcohol to give us our carboxylic acid to our primary alcohol if we use sodium borohydride. Okay. So this is the type of strategy I want you to start thinking about as you go through the homework on here. How can I get selectively to it? And if I used a different reagent, what would the product be? Okay. So I'm going to open it up for questions on strategy. Yes, Clay.
Is that a hydrogen in the is that a hydroxide right there?
Okay, this, yes, it was an ester when I did the first reaction, but now it's a hydrogen because when I did the second reaction, because if in this reaction here, it's a hydrogen because the hydrogen was already there, and the carboxylic acid is not affected by sodium borohydride.
Okay. And then right there in the left top corner of the screen, that's an H next to the O.
This, yes, is an H.
Yeah. Cool. Thank you.
Sorry, the stylus on my my pen here is a little big and it's hard to get right sometimes. I'm looking for.
Okay. No worries.
Okay.
I have a question.
Yes.
So in the original reaction, like the original reagent, you like with the ester, were we trying to only reduce the ester?
On this one right here with the sodium borohydride, the ester is not reduced by the sodium borohydride. It only reduces the ketone, and you maintain the ester. So I'm drawing it wrong. You keep the ester on it with sodium borohydride, but because it was already a carboxylic acid over here, you keep the carboxylic acid and you only reduce down the ketone. Okay, in both cases, the sodium borohydride is only reducing down the ketone. It does not affect the ester or the carboxylic acid.
If we wanted to reduce the ester, then we would use LAH.
Yes.
Okay.
Yeah, that is our only reagent right now that will reduce down an ester or a carboxylic acid. Okay? Yeah, but remember, one of our reagents reduces down acid chlorides to aldehydes. So that's the sodium borohydride. If you had a carbonyl with a chlorine on it, it reduces that one down to an aldehyde. But that's not on this slide. It's just one of those reagents we have that gets us to aldehydes as well. Okay? Okay, I'm going to stop sharing real quick. There we go. And go ahead and open up for questions. Okay. Okay. If you're shy, let me go ahead and stop recording and